So let me continue where I left off. A little bit of it as a reminder. So we have beta decay now, which we started from the beginning. Reaction that I said we don't even today, trying to explain the 888 seconds is not an easy task, and there's theoretical physicists that try to do that. So we have beta decay, but we also have inverse beta decay. And when we start looking at neutrino interactions, then we're basically looking at the same classical thing that I started with, neutron beta decay, or the beta decay of some object. You run it backwards or sideways, you can see it's the same particles. So when we start talking about neutrino interactions, the physics, if I draw the diagrams, is related, or it's really the same physics. The probability of this interaction, so as I showed you, is really the second ones. The neutrino ones are very low because the neutrino cross-section is so low. Therefore, we need lots and lots of neutrinos, or we need neutrinos at very, very high energy, which we get from particle accelerators. So when we talk about studying neutrinos and particle accelerators, we can get neutrinos that are high enough energy that these cross-sections become larger. The cross-sections actually, I'll show you later, but they basically grow linearly with the energy. If the energy is high enough, we can get a lot of interactions. And in fact, for me personally, I spent quite a few years studying neutrino interactions at a high energy accelerator because using the accelerator, we could get so many more that we could study their properties very well. And we studied something called the neutral weak interaction at that time. Anyway, going back to the history, Reines and Cowan did their final experiment not on a nuclear explosion, but on a nuclear fission reactor, and they presented the first evidence that neutrinos actually had been observed. And again, as I keep emphasizing, even though we had 30 years of predictions of neutrinos, we've seen in the case of supersymmetry, which I showed you last time, that it doesn't necessarily follow that we develop theories and experiments are just a check. It's very important to do both. We don't believe in physics results until we somehow are able to see them in the laboratory, or we see things in the laboratory that we then have to develop theories to explain. So doing physics is constantly a back and forth between theory and experiment. So this is the details of what they use. They use this cleaning fluid, but there's roughly quite a lot of 200 liters of cleaning fluid that they used in order to do this. And they did some tricks electronically just to give them the credit of looking for a delayed signal. What do I mean by that? The neutrino interacts, but to see the reaction that I showed you that happens in the interaction, there's some lifetime involved, or the actual signal comes out later. That turns out to be a unique way to look for something. See it happen, and then you look for something that's supposed to happen later. It tends to be a strong way to actually identify what you're looking for compared to something very different. So this is a picture of what they looked at. The neutrino comes in, it interacts. When it interacts here, comes into their apparatus, coming from a nuclear reactor. When it interacts, it makes a positron, which I show this way, and that makes a signal. But then they make something else which decays later, and they see a late signal. And it's a combination that gave them the ability to actually know that what they saw was unique and stood out over any possible background. What happens on this side is that the particle, the neutron goes out, it finally interacts, and when it interacts, it makes a whole bunch of gamma rays, and those gamma rays it interacts, it's actually captured by cadmium, and then it emits all these gamma rays which you're seeing. So you see the first signal from the electron, and then sometime later, you see the second interaction, which releases those photons. And that was the scheme they used. This was the picture that I showed you. And what you can see on the very bottom kind of summarizes how convincing or not convincing this first result was. They ran with the reactor turned on, and they saw about one presumed picture that looked like this each hour. Then with the reactor turned off, they saw about a quarter of that rate. And that was the difference, which after they ran enough to determine those numbers accurately, was their evidence that they had seen neutrinos to interact for the first time. The next thing is, and this starts to become more complicated, as I said before, for those of you that don't quite know what we mean when we're saying things quantum mechanically, I'll try to say them in words. And that is that all these particles have something we call spin. So you can, if you don't know the quantum mechanics, which forces the spin to be particular units. The spin can be a half a unit or no spin at all. So these things, when I say a half a unit, just tells you that quantum mechanics forces it to be specific. But if we then look at the spin of these particles, then as I mentioned, what we found is that the spin actually goes with a particular direction. And I'm going to come to first. We've seen neutrinos. That was done in this very first experiment. And then a second experiment for the first time saw anti-neutrino, or tried to see anti-neutrino. And if the neutrinos were the same particle as the anti-neutrino, then, which maybe it is, because it's a new kind of particle, then they should be able to see using the same kind of reaction down here. The neutrinos and the anti-neutrinos, you remember the other one, had to be an anti-neutrino interact, but they basically did this ambitious experiment and saw that they didn't see the reaction. And so the anti-neutrino was not the same particle as the neutrino. But interestingly, there was a rumor that spread, this is often in physics, or at least this is the story. The rumor that spread before this experiment was done was that they were seeing the anti-neutrino and the neutrino reaction. And that spread even to the Soviet Union at that time, or Russia. And the fact that it happened got to Bruno Pontecorvo, who was the, I don't know if he's in that picture, was one of the Italian physicists from the 30s who went first to America and then left and through Canada and Finland and ended up in Moscow, in Dubna, near Moscow. And he was a very brilliant physicist who, in hearing this rumor, developed the idea that maybe neutrinos have mass and change identity and change from one to another. And that was why this would happen. So he projected that maybe neutrinos have mass way, way before, for very different reasons, people found that neutrinos have mass much later. It had to do with neutrinos coming from the sun, and I'll show that. But he not only projected it from the wrong reason, maybe, because this turned out to be, as you see, they were not observed, there was a false rumor, but he developed the whole phenomenology of what would happen if neutrinos had mass, because they could change identity from one to another. So before we ever had the real reason to develop what happens when neutrinos have mass, he had developed it for maybe wrong reasons, but he developed the phenomenology correctly and published it. So basically, he's the person who proposed first that neutrinos, if they have mass, we'll come to that later, actually change identity if you let them go through time. They'll change from one kind of neutrino to another, and we'll come to that. Okay, so let's continue. Neutrinos have some spin. I've indicated that down here. Picture down here. So the neutrinos themselves, just to emphasize, do not feel the strong force. They're a product of weak decays. They don't also experience the electromagnetic force. So they only decay weakly. That's the first reason that they're so hard to see or detect. In the standard model, let me emphasize that again because we're going to talk about mass. In the standard model, even with the Higgs, they don't have mass and they move relativistically at the speed of light. Now, I'll show you a picture in a few minutes that if they have mass, that creates a little bit of a problem. So, as I said, Pauli then described that their neutrinos exist. He wrote this letter. Fermi developed a theory, which I've shown you, and we've discovered the neutrino. So that's where we are. And now I want to go on. So remember that the neutrinos are produced by beta decay. The antineutrino, and that's the antineutrino, not the neutrino, because we have to conserve the number of particles. Since the electron is a particle, then it has to be the antineutrino. The difference between the antineutrino and neutrino, what is it? Recall that the photon is its own antiparticle. The neutral pion, one of the particles we looked at, is also its own antiparticle. There's no anti-pi zero. There's no anti-photon. On the other hand, the neutron is not its own antiparticle. We have antineutrons. So what about the neutrino and the antineutrino? That's what was the question when Reines and Cowan developed the detection of the antineutrino. And that was when Davis and Hammer looked for the same analogous reaction with antineutrinos, but they didn't see any. That told us that somehow the neutrino and the antineutrino are distinct particles. And you might remember back a few lectures that I talked about in the weak interactions that there's a conservation principle which has to do with conservation of lepton. And so that's the reason that these aren't seen. Actually, whether the neutrino is its own antiparticle, the way I worded it, is a separate question, and it's unanswered at the present time. It matters for some important theories in physics, and there's very ambitious experiments here in Italy, actually, to try to determine whether the neutrino is its own antiparticle. And I'll come to that a little bit later. So antileptons are produced by the positron, and neutrinos have different lepton numbers. I said the lepton numbers are conserved, and that's just an empirical rule. When I showed it to you, I never showed you a theory that said there are these lepton numbers and they're conserved. It comes out of observation only. And so it's one of the pictures that's unsatisfactory in this standard model. If you have a conservation law, like conservation of lepton number, it shouldn't come just because we experience it and then make up a rule, but that's what's done here. So we don't have the complete, despite the fact that we have this picture that describes a lot, which we call the standard model. That's one of the reasons it's called a model and not a theory. It doesn't describe a lot of what we have put in empirically. So there's other puzzles as we look at the story of the neutrino, which I'm doing now, that unfold. The reaction mu goes to E plus a gamma ray is never observed. That's because of this lepton number and electron number and muon number. And the consequence of that is that there's lepton number conservation. Some processes are just not allowed. So we can look at neutrinos, and they should have conserved lepton number. That means that we should not, or we should see certain reactions when we start looking at neutrinos, which are pretty interesting. So if I'm able to make neutrinos, and they're a particular type, so what's written down here is a muon neutrino, what's written here is an electron neutrino, or an anti-muon neutrino, electron neutrino, anti-electron neutrino. They come about because of the decays reaction that are shown. So this reaction happens. This one doesn't happen because it doesn't conserve lepton number. This doesn't happen. This happens, but this doesn't happen. So notice, if I have a muon neutrino, it'll make a muon, but not make an electron. If I have an electron neutrino, it'll make an electron, but it won't make a muon, for example. So the experiment that was done was one that I showed you, but you probably don't remember, when I was showing you something about equipment. And I was trying to show you that advances in equipment lead to advances in discovery. One of the ones that I showed you that you probably forgot is the experiment of Letterman, Schwartz, and Steinberger, which was done at Brookhaven Lab. And it was done to test this very bottom hypothesis here. And the idea was to make neutrinos of a certain type and see when they interacted whether they remembered how they were born, come out of beta decay, by making the same particle in its interaction. And so they made what they knew were muon neutrinos because they made them in a decay that involved the muon and not the electron. They saw a decay that had a muon and not an electron, so the neutrino was a muon type neutrino, and then they looked to see if they, in the final state, would see electron or muon. And indeed, to me, a pretty interesting experiment where you had the interaction in the end, and you saw that the particle, this neutrino, remembered somehow how it was born. It was born in a decay that involved a muon, and when it then made an interaction, it made a muon. And that basically was due to this lepton number conservation, which, as I say, is which doesn't come from fundamental principles, but seems to be very, very well obeyed. So this is just writing down how that works, and that experiment was done. So now returning to the four fermion interaction. This was Fermi's interaction. The next question to consider is the polarization or the parity of these interactions. So the next thing I'm going to talk about is once the neutrino is found, and we have Fermi's theory, the next thing that was studied is whether we have conservation of parity. So what do I mean by that? That's conservation. Simplest way to think about it is what we do as a person. If we look in a mirror, we see a mirror image of ourselves. Is that mirror image of ourselves truly a mirror image of ourselves? Or is something screwed up about it that doesn't reflect? If there's a violation of a perfect mirror image, then we get a violation of parity conservation. And in certain processes, not ourselves looking in a mirror, but certain processes in decay, we could have the possibility of parity violation. This possibility came about because of a theory of weak interactions that was developed, as I'll show you. So first, there were some other puzzles that were found. So where I'm trying to kind of show you the parallel developments, kind of where physicists were thinking at a particular time. So all these particles that I talked about that were being discovered, you never saw this one listed on what I showed you. But there was a little puzzle, and that, not so little. There was a puzzle that there were two particles that, as accurately as they could measure them, were the same mass. But for some reason, they were distinguished because one of them decayed into 3 pions, and the other one decayed into a pi plus and pi zero. And so that was a puzzle. Is it one particle? Is it two different particles? Before we knew, because their mass was the same, they just were given two different names, the tau and theta, and we had what we called the tau theta puzzle, using the label there. This lasted for maybe 5 years or 10 years, that there was what appeared to be the same particle in production, because everything you could measure about its production was exactly the same, mass and so forth, but we had two distinct results. Then they looked at the decay products, because I talked about parity, and they saw that the parity of the two were different. One had parity in one direction, one parity in the other direction, which meant they weren't exactly the mirror image of each other. And so there was some feature of this, this is the first hint of this parity problem that exists in weak decays. And so the resolution of this was that either the tau and the theta, these two particles, have the opposite parity, therefore they're different particles, or parity itself isn't conserved in the weak decay. So that was the dilemma that existed at that point. Do we have a theory, do we have a hint here that parity maybe isn't conserved? There's no way to tell, but there's a hint that this is the same particle, but can go in both, give both a plus or minus parity, two different kinds of decays, or was this just an accident and it's two particles? That was the puzzle at this time, which was like 1960 or something. And a famous physicist at the time, I quote here, he said, "I find myself unable to withstand the local pressures against any hypothesis of parity non-conservation." The argument against it was that parity violation was simply inconceivable, and it was nonsensical even to mention this possibility. So among physicists and among ourselves, in kind of intuition, we expect when we look in a mirror, we're going to see ourselves backwards, that somehow we haven't found a place in physics that likes to violate that principle. And so there was resistance, as there always is, to change. But in 1956, Li and Yang came along, and they suggested that particles are the same, and that these particles are the same, and that parity is not conserved. So they took on the problem of exactly this decay and decided to create a theory where parity is not conserved. And that turned out to be tested by a colleague of theirs named Wu the next year, and she showed that parity is not conserved in the beta decay. Beta decay is a weak decay of a particular nuclei, cobalt, and not only does it happen, as I'll show you, but it's maximally violated. So the tau and theta were then accepted as the same particle, and it's just called the K plus. So we have one particle. When you look at the tables, it's called a K plus, but it has this history that because it has these two different decay modes, people were stimulated to question whether parity is conserved in the weak interaction. So this little cartoon is a picture of what we're talking about. This is Madame Wu and T.D. Li and C.N. Yang when they were a little younger than today. I think Yang, who's shown here, is now 97 or something, 90. He happens to have a wife that's 30 or so, but he's 97. And T.D. Li is still alive but ill, and Wu has died in the meantime. Anyway, she did the experiment, and they did it where I've shown in the picture here, kind of mirror of each other. And the question is does the mirror particle or person the same as the other one? And so she proved that Li and Yang were right, and that solved this so-called K on decay puzzle and predicted that weak interactions are violated parity. The interesting thing is not only is it violated, but it's maximally violated. So like you look in the mirror and you see not the mirror image of yourself, but just the opposite. You become the person becomes opposite in every way. Okay. So this is her result, which I don't have time to go through, but it basically, I'll describe, translates into, in a certain decay, the particles go backwards instead of forwards, which is what she saw. You want to go just the opposite direction to what you expect, and that had to do with this spin direction, not behaving that way. So this was the maximum violation that she saw. It's shown here in that on the bottom we have a particle that's spinning and it's moving at a certain velocity, and the question is, do the decay particles spin in the same direction or not as the original particle? And they want to go in the opposite direction, which is strange, but that was the maximum violation of what you expect to happen. So, so this was tested in various ways. I'm running out of time, so can't go through some of the checks that are there. But the next question really had to do with the fact that how big was this violation? And so this is the experiment that looked at whether spin wanted to go in the same direction or the opposite direction, and it was measured. I didn't have time to go through the experiment. It was done by a physicist named Goldhaber, and it wanted to go opposite to the direction you expected it to go with about a 30% error, and that was a really important experiment to change how we looked at things. This is the picture, the experiment itself, and the result, so we're sitting now, is that neutrinos themselves are, like if they were a screw, are spinning in a left-handed direction. Left-handed screw, and this is the famous paper, which was 1957. So neutrinos are moving in a particular direction and spin in one direction, and you can see in the bottom right hand that if I have an anti-neutrino, it spins in the opposite direction. And that's what we knew after this set of nuclear physics experiments that looked at that. This creates now a problem, which I'm just going to put up front ahead of time, if we think that the neutrinos might have mass. So the prejudice that they don't have mass, despite the fact that somebody like Pontecorvo had developed a theory, is pretty simple to see. If we look at a neutrino in this top picture, it's going left-handed. We just did the experiments to see that it's left-handed, spinning in the opposite direction of a screw that you screw into the wall. Now imagine that you move at high speed. If you move at high speed, you can go faster than the neutrino if it has mass. Because if it has mass, it can't go as fast as the speed of light. So I can go faster than it. But then in my frame of reference, looking at it, it would look like it's spinning in the other direction. So now the neutrino all of a sudden becomes right-handed. So the arguments for a long time, maybe I should repeat it, if it's spinning, it's left-handed. But now imagine it has mass. If it has mass, I can watch it go by me, and it's spinning and it's left-handed. But now if I go alongside of it, and in fact, if I'm going faster than it's going, and I look back at it, it'll look like it's spinning in the other direction. So since we can't have right-handed neutrinos, they have to be left-handed. This was the argument used for decades that neutrinos should have no mass, or the strong prejudice they should have no mass. This turns out to be, again, an illustration that nature doesn't always follow your prejudices or your theories or ideas. So this was the simple-minded argument that dates back to the 1960s that the neutrino shouldn't have mass. And it wasn't for 40 years before we really determined that neutrinos do have a tiny bit of mass, even though we don't know where it comes from. So, the detection of the muon neutrino, let me show you again. I showed you this when I was showing you the equipment, but now I want to show it to you from the point of view of the discovery itself. So the idea is that protons scatter on a target, and they make pi mesons. Pi meson. And the pi meson, when it decays, if I put a detector, I can see or detect that I have a mu meson here. And I do that by usually putting up some material where it stops and I detect the muon. So if I detect the muon, then when this decayed by what I showed you earlier today, this should make a muon neutrino. And by the hypothesis there's different identity for these neutrinos, or conservation of lepton number, which we didn't know for sure, then when this neutrino interacts in material here, it should remember how it was born. It was born with a muon and not an electron, and therefore it'll interact, making a muon in the final state. And that's exactly what was found in the experiment. And this was the experiment. I showed you this apparatus, called it a spark chamber, and it was done in an experiment by Letterman, Schwartz, and Steinberger in 1962. So, to summarize then, we have a conservation of lepton number. We don't know whether the neutrino is its own antiparticle, even though the early conclusions were that they're their own antiparticle. And we developed then a new problem in 1968. So in 1962, we determined this lepton number, and then in 1968, a new problem developed, which I'm going to explore after the New Year's in a future experiment, future lecture. And that is that, okay, we somehow now understand a lot about neutrinos. We know there's different ones, electron neutrino, a muon neutrino, and a tau neutrino, presumably. We also think we know how the sun burns by a nuclear fusion process. And in fact, you can do the nuclear physics so accurately that you can tell what the temperature is at the beginning, middle of the sun, and the features of the sun, and how much energy is radiated. It's all consistent. So the picture of how the sun burns, or stars burn in general, is the nuclear fusion process. Nuclear fusion, we know, is a bunch of nuclear physics reactions, which I'll show you later. And out of that, the primary particle that comes is, again, just like I looked at now, and not the muon neutrino that Letterman and Schwartz looked at, and Steinberger, but the electron neutrino. So if I have electron neutrinos that come from the sun, I know how hot the sun is, I know how many neutrinos are made, I know how far away the sun is. Neutrinos should come to the Earth. It was a great feat, really, when they made an experiment that actually for the first time saw neutrinos from the sun. I'm going to show you that experiment. You know that it's right because you can do it like astronomers and see, and actually the experiments are good enough to point so that you can see an image of the sun with these neutrinos. And the problem, which I'm going to show you, is that there were not enough neutrinos by a big factor, roughly a factor of 3. So there are a variety of experiments. They looked at neutrinos at different energies, and they saw for the first time that there were neutrinos from the sun. This proved the conjecture of fusion, and somebody won a Nobel Prize for it. But what happened is the number of neutrinos detected were too small. This was a huge problem for physics. How do we explain it? Either we don't understand. So there were two schools of thought, and I'm going to end on this today, and then we'll proceed. There were two schools of thought. One of them, both logical, one of them is that somehow there's something wrong with the nuclear physics as we understand it, and it's quite complicated in calculating all the interactions and the distributions of heat and nuclear interactions that happen in the sun. So there's something wrong with it. It gives the wrong number of neutrinos. And there were various stimulated the various ideas for what might be a different, somewhat modifications on the process, none very satisfying. And so one explanation was that, usually made by particle physicists blaming nuclear physicists for not being able to calculate properly the nuclear fusion process. And then on the other side, because I went to a lot of meetings like this and they'd argue, on the other side, the nuclear physicists would claim the particle physicists didn't understand particle physics well enough. And so the other possibility is that the neutrinos actually don't get to the Earth, even if they weren't born at the sun. And that turns out to be the true case. They do get to the Earth, but by the time they get to the Earth, they're no longer, say, an electron neutrino, but they've changed identity to a muon or tau neutrino. I'll explain to you how that happens in a future lecture if you come back. And therefore, there's three kinds of neutrinos. Remember, three kinds of particles. The sun's far enough away so that basically, by the time it gets to the Earth, whatever the particle was born, by the time it gets to the Earth, it's equally populated, electron neutrinos, muon, and tau neutrinos. So if you have a detector that's only looking at electron neutrinos, you see roughly a third of what you expected to see. And that, as I'll try to show you, was the final resolution, not to leave it as a mystery, of the problem. We do understand how the sun burns, but the neutrinos actually, through something that Pontecorvo talked about 50 years before, actually change identity by what we call oscillating from one kind to another because they have some mass. But I told you they can't have very much mass because they create a kind of inconsistency problem when we talked about the way they spin. So we have to resolve all that, and we'll do it as the next lectures. So that's it for today. Thank you.